Imagine seamlessly 3D printing complex, optical grade silica glass components. Things like ultra-precise diffractive optical elements or high Q factor topological photonic systems. Now imagine doing that at like 7 times your usual print speed.
Yeah, and completely free of staircasing artifacts, right?
Yeah.
Which for anyone doing two-photon polymerization, you know that sounds, well, basically impossible.
Right, you always have that agonizing trade-off between print speed and surface quality. But welcome to the 2PP podcast. Today we are doing a deep dive into a 2026 Advanced Functional Materials paper by Schneider and colleagues that actually makes this application dream a reality.
It really does. We are unpacking how two-photon grayscale lithography, or a 2GL, applied to a custom inorganic resist permanently shatters that compromise for your next fabrication run.
But to achieve these dream applications, we first have to solve what they call the inverse problem, right? Like dynamically scaling voxels for inorganic resists.
Exactly, because how do you dynamically change the size of your printing building blocks, the voxels, using continuous laser power modulation? It is incredibly tricky in an inorganic material.
Okay, let's unpack this. So traditional layer-by-layer 2PP is, it is basically like building with tiny, rigid Lego bricks.
Right, you always end up with those jagged stepped edges.
Yeah. But 2GL is more like a digitally controlled extrusion of clay. You turn up the laser power, and the voxel dynamically changes volume, bulging out to fill empty space and, smooth out the contours.
Yeah, and to pull off that clay effect in glass, the researchers engineered a pre-glass polyhedral oligomeric silicic-squioxane resist, or POSS for short.
Right, POS.
And they paired it with a highly sensitive Nourish Type 2 photoinitiator called BBK. This specific combination is what gives them the massive dynamic range they need for 2GL.
Because you need a huge window between the exact laser dose that cures the material and the dose that just boils or damages it. Right?
Exactly. And they mapped this all out using a brand new 4-step parameterization routine.
Wait, how does that routine actually work? Because if the material is custom, the printer doesn't just inherently know how it's going to react.
Right. So first is a dose sweep to find the absolute limits of the resist, where it cures and where it burns. Then a 2PP sweep establishes a baseline using that standard Lego brick printing.
Okay, so that gives you your standard parameters.
Yep. Third is the 2GL sweep. They slice the model coarsely to print really fast, and then tweak the grayscale laser modulation until those coarse steps literally melt together and disappear.
Oh, wow. That is wild.
Yeah, and finally there is a voxel compensation step. When you pump in more laser power, the voxel doesn't just get wider, it stretches vertically too. So this step corrects that elongation so your print actually stays accurate.
Here's where it gets really interesting though. Once they lock in the material and the printing parameters, the physical performance is just insane for high-end micromechanical applications.
Oh, absolutely. The paper reports a Young's modulus of 71 gigapascals and a compressive strength of 5.5 gigapascals. But wait, wouldn't such rigid glass structures just instantly shatter at the microscale under any real strain? I mean, it's glass.
You would think it would snap, but at this scale, we see something called extrinsic size effects. When you shrink glass down to the microscale, there physically isn't enough volume for the microscopic cracks and flaws that normally cause glass to break.
Wait, so it just bends?
Yes. Because it is so flawless, these micropillars can actually endure about 22% strain via post-yield buckling before they finally fracture.
That is a massive amount of deformability for glass.
It is. And crucially, these 2GL printed micro-tuning forks hit mechanical Q factors of nearly 1,500 after they were converted to glass.
Wow. And commercial polymers sit around, what, 29?
Exactly. So if you are building low-damping mechanical metamaterials where you cannot afford any energy loss, this POSS glass is ideal.
So what does this all mean for optics? Because beyond mechanics, the ultimate proving ground for eliminating staircasing is optics, right? Even nanoscale roughness completely destroys performance.
Oh yeah, it is the ultimate test. I do have to push back a little on them calling this optical grade, though. Is a 3D printed lens actually competitive with traditional top-down etching?
It actually is. The printed aspherical microlenses boast a root mean square roughness below 3 nanometers.
Below 3 nanometers. Without any post-processing.
Without any post-processing at all. Furthermore, they printed a 160 micrometer diffractive optical element that cleanly projects a holographic logo.
That is incredible. And because it's silica glass rather than a polymer, it offers superior thermal stability too, right?
Yes, and a much higher laser damage threshold. If you are working in high-power photonics, polymer just melts. You absolutely need glass.
Right. So to sum this all up, We've explored how pairing a custom BBK-initiated POSS resist with that four-step 2GL parameterization routine unlocks high-throughput, flawlessly smooth glass fabrication.
It really takes all the guesswork out of grayscale printing for custom inorganics.
It does. Which leaves us with a wild thought for you to ponder before your next print run. If this routine successfully solves the inverse problem for custom POSS class, what happens when you apply this exact workflow to experimental multi-material or conductive hybrid resists?
Oh, that is an exciting idea.
Right. Could we soon be 2GL printing fully integrated single-print optoelectronic circuits? That dream of flawless hyperfast printing might just be the beginning.